You know, physics and chemistry are usually taught as two sides of the exact same coin. But beneath the surface, there's actually a deep and honestly often misunderstood philosophical friction between the two. Welcome to this explainer. Today, we're diving into a really fascinating presentation by Dr. Giovanni Villani. We're going to trace a journey from the absolute smallest building blocks of reality all the way up to these massive philosophical questions about how we actually define the microscopic world around us. So let's just get right into it.
Here's our roadmap for today. We're going to hit the atomic revolution, see how quantum mechanics enters chemistry, tackle the molecule problem, look at visualizing the invisible, confront the philosophical divide, and wrap up with the quantum horizon.
All right, part 1, the atomic revolution.
Just look at the sheer speed of discovery here. It's wild. In just a few decades, science zoomed from literally just discovering the electron and radioactivity back in 1896 right through to completely redefining atomic structure. I mean, we see early models popping up between 1904 and 1911, and then bam, Niels Bohr revolutionizes everything with his quantized orbits in 1913. By the 1920s and 30s, the introduction of early quantum mechanics just entirely shattered the classical view of the atom. It was this incredible golden age of physics that fundamentally changed how we see the universe.
Moving on to Section 2, quantum mechanics enters chemistry.
So how did those foundational physics theories eventually evolve into entirely new chemical capabilities? Well, in the mid-1920s, Heisenberg and Schrödinger introduced some intensely complex math to describe particle behavior, specifically matrix and wave mechanics. And these were essentially just advanced mathematical tools used to predict the incredibly weird, wave-like behavior of quantum particles. Initially, sure, these were purely physical models. But as we move along to the 1950s, this brand new interdisciplinary field called quantum chemistry is born. And from the 1980s right up to the 2020s, we see modern supercomputers calculating molecular properties and interactions with just astonishing precision. We have literally gone from chalkboards to massive server farms, bringing physics and chemistry closer together than they've ever been.
Which brings us to Section 3, the molecule problem.
Because since the 1920s, right alongside all those brilliant atomic discoveries, scientists were facing a massive theoretical roadblock. The central question was basically this: what exactly held a group of atoms together to form a molecule? It sounds so straightforward, right? But from a pure quantum perspective, it was unbelievably difficult to answer mathematically.
The crucial point here is that understanding a single isolated atom didn't just automatically explain how they interact and bond to create complex molecules. Honestly, even back in the 19th century, way before quantum mechanics, the molecule was a profoundly difficult theoretical problem. You can't just take the math for one atom, multiply it, and instantly understand a whole molecule. It's kind of like knowing exactly how a single brick behaves under pressure, and then expecting that to fully explain the architecture, the sway, and the structural integrity of an entire skyscraper. The complexity scales up in ways that the simpler models just couldn't handle.
And that leads into Section 4, visualizing the invisible. Notice the stark transition here. We're moving from a relatively simple, clean ball-and-stick model that shows basic atomic connections to something that's incredibly dense. As we start looking at complex mappings like proteins, we're dealing with really intricate topographies. You have to start tracking electrons that are shared across the whole structure, what we call delocalized interactions, rather than just electrons pinned down locally between two specific atoms. At this scale, the properties of the whole system start to shift entirely away from just the properties of its individual parts.
Visualizations like this, absolutely beautiful, colorful ribbon diagram of a complex protein structure, really show just how far we've had to zoom out to model these entities effectively. When you look at this, you're not even seeing the individual atoms anymore, are you? You're seeing folds, helices, and overall functional shapes. This right here is the chemist's view of the world. It focuses on the macroscopic form and function, and that requires completely different ways of thinking compared to the microscopic reality beneath it.
Okay, Section 5, the philosophical divide.
Because moving from the atom to the molecule, it wasn't just some tricky math problem. It introduced massive problems with how we actually acquire knowledge, real epistemological hurdles. Scientists suddenly had to deal with the symmetry of systems and the very definitions of structure and form. It essentially forced chemists and physicists to grapple with entirely new types of approximations, the absolute limits of their mathematics, and a major shift from looking at historical component properties to analyzing global steady states. Let's actually break down a couple of these bigger ideas.
You know, there's that old joke that physicists assume everything is a perfect sphere, like a spherical cow in a vacuum. And honestly, that's basically true here. The physicist's ideal is the neat, highly symmetric, solitary atom. It's elegant. It's mathematically beautiful. But chemistry? Chemistry has to deal with the messy, shape-shifting asymmetry of interconnected molecules. An isolated atom is essentially just a sphere, but a molecule is the smallest true object that actually possesses a distinct, complex shape. And as any chemist will tell you, shape dictates absolutely everything.
Furthermore, we're practically forced to choose our lens. Do we look at global properties? That's the pure quantum approach, where the entire molecule gets treated as one giant, inseparable cloud or wave function. Or do we rely on component properties, treating the molecule like a Lego set of distinct atoms held together by separate, identifiable bonds? This isn't just semantics, folks. It's a fundamental clash in scientific philosophy.
Which leads directly to what I think is the most profound question of this entire explainer. Are there even atoms in molecules? Seriously, take a second to really think about that. Once an atom bonds into a molecule, its electrons are shared. Its quantum state is completely entangled with its neighbors. So does it even remain an individual atom, or has it dissolved into something entirely new? The strict physicist might say the individual atom is just lost to the molecular wave function. But the chemist insists the atom absolutely must still be there, acting as a component so we can predict reactions. It's such a fascinating paradox.
This brings us to our final section, the quantum horizon.
Today, advanced technologies and brilliant scientists are actively expanding our understanding of these molecular interactions. By integrating innovative theoretical models with just massive computing power, we're seeing breakthroughs that literally impact your everyday life. This exact science is what drives the development of next-generation medical drugs, the creation of stronger, lighter materials for your smartphone, and vital advances in biology. We are currently simulating chemical reality at a resolution that past generations could only dream of.
But here is the fascinating twist. Despite all of this amazing progress, all the computing power in the world still hasn't resolved the fundamental conceptual differences between the two approaches. Ongoing research brings quantum mechanics and chemistry closer together practically, allowing us to build amazing things, but it doesn't resolve the deep philosophical problem. The physicist's holistic, mathematical atom and the chemist's structural, component-based molecule are still speaking slightly different languages. We have much better approximations now, sure, but not necessarily a unified underlying philosophy.
So, if this philosophical friction sparks your curiosity and you really want to dive deeper into this complex but incredibly fruitful relationship, you should definitely check out Dr. Giovanni Villani's in-depth 2025 analysis. It's published in the Top Italian Scientist Journal as an overview celebrating the year of quantum sciences and technologies, and it really expands on all these concepts in beautiful detail. Which leaves us with this final thought for today's explainer. As our technology continues to evolve, and as supercomputers allow us to calculate molecular properties with unprecedented, almost unbelievable precision, will we finally bridge this philosophical divide between the isolated atom and the complex molecule? Or is a molecule, at its very quantum core, truly forever greater than the sum of its parts? Thanks so much for joining me on this journey. Keep questioning, keep exploring, and I'll catch you on the next explainer.